All right, everybody see the board all right with the camera there? Yeah? Well, this round doesn't impact us. Everybody see career fair on the 26th?
Career fair I thought was tomorrow. Maybe it's down the road.
26th.
26th?
Yep. Yep. Yeah, Rob sent the email yesterday. But yeah, it's for the 26th. So just thing to keep in mind is that's an all school, right? So not necessarily going to be construction focused, but.
Are we doing that breakfast again?
Breakfast is the 27th. I sent you an invite already, didn't I?
Yeah.
Not losing my mind?
No, I just,
Okay.
I'm looking it up.
Yep. So, and as a reminder, I talked with Jing, for those of you in her material science class, neither of those classes will be meeting that morning, okay? So we'll just be at MCC for breakfast. So, had a good meeting with them last Friday. Actually, it was with ACI, the American Concrete Institute, on more ways that we could get the concrete folks involved in the program. But it was interesting to hear. We had a couple Dunwoody students there. Interesting to hear. I guess I thought that I've done a good job of getting concrete involved here, but there's certainly always opportunities to improve. So, okay, talking about shear. We looked at a couple problems last week. You're to do a little bit of reading. The terminology quiz is open. Have you tried any of the homework? Do you have any questions at this point, or do you want to just look at a couple more examples?
I didn't find any homework on there. There's nothing.
Oh, good. It certainly could be the case that I would forget to unpublish, or forget to publish.
The terminology is unpublished.
Good. Makes it easy for you to complete them.
I don't know if it was like, you don't unlock it till we talk about it in class.
No, just the usual crippled by technology. So give me a second, I'll get it unlocked.
It doesn't help.
What's that?
So the 6 classes doesn't help.
There's that. There's certainly that.
Oh, I didn't do it either. Shit. I didn't act.
Do you allow late work for construction contracts?
Yeah, I mean, that class is gonna be such a disaster, so.
Why do you say that?
There are cameras on. I actually, next Monday will hopefully be the saving grace for that class, because we don't have classes, so I'll be able to actually get stuff out for you. I will have stuff out today, but actually get a couple weeks worked ahead. Okay, so we need this.
This one's like the occasional space. No, that's single space. I think I would know. I have written plenty of papers. What? It might be.
The receptionist for that McDowell company, oh, you should give him a call. He's one of the funny ones.
That's fine, we'll just keep you like that.
Is that the mechanical contractor?
All right, so now the terminology quiz and the shear homework will be open for you. Thing to keep in mind is, for the shear homework, it's on there as assignment number 4, right? We've only done 2 assignments to this point. The reason being, the assignment 3 that I've done in previous times that I've taught this class, method of section, method of joints, it just bogs us down for far too long, okay? So we can get into other types of material. First of all, it clears us off to go to the breakfast meeting. It'll allow us to do other stuff in lab, look at recycled materials, things like that, okay? So, which I think will be of more benefit to us. So we probably then just need to today talk a little bit about shear, look at a couple more example problems. So let's think about shear in general. Okay, what are we talking about? How are we impacting our materials when we're trying to shear them? What are we trying to do to them? Remember last week I had the piece of paper?
I didn't know what the was.
Right? Is it easy for me to shear this material? Not this particular material type, right? But it's easy for me to bend this material, okay? What about the paper? Is paper gonna shear pretty easy? Typically does, right? Okay, so shear is when we have forces acting in opposite forces to each other, okay? And so we're typically mostly concerned about shear in beams, columns, girders, those types of things. Actually, that's not true with columns. We're more concerned with buckling in columns, but beams and girders, okay? And remember that the first thing that we talked about was direct shear stress. And then we talked about shear in our beams, okay? So what we looked at when we looked at the direct shear stress is we talked about saying that we're connecting two pieces of steel beam with a plate that we're going to bolt, okay? So the idea is the bolts are coming into and going into the lab space right behind us, right? So we have some sort of force acting on this, and our shear stress we're denoting with the letter V. It equals our force divided by our cross-sectional area, okay? So if we looked at our force being 7,500 pounds, and we said, well, if we know that the shear capacity, or the Vmax of this steel, which I don't know anything about shear capacity off the top of my head, but if we said that, well, yeah, well, we got a bunch of goofy bolts in here, so let's keep it with steel. Let's say the shear capacity is 20 KSI. Just use that, it's a nice round number. Don't quote me on its effectiveness as being true to shear capacity, okay? I don't reference my steel design manual all that frequently. What would we have to do? What are we trying to determine if we know these values?
The area?
We would have to determine the area of steel to bolt that thing in place. Okay? So how would you rewrite this equation?
Divide by P. Times by A.
Multiply both sides by A.
Yeah.
So AV equals P.
Because it always cancels.
Yep. Anything else you want to do?
Divide the V.
Divide both sides by V.
Yeah.
Yep. Okay, so our cross-sectional area is going to equal our force divided by our shear. Okay? Conceptually, that should make sense to us. Here we have pounds. Here we have pounds per square inch, right? Our pounds are going to cancel, and our inches move up into the numerator. Sorry, our square inches move up into the numerator. Everybody comfortable with me giving you an area in square inches? You can visualize that, what that means? Okay? So then it's just plug and chug, right? So 7,500 divided by, what did I say, 20,000? Does that give us 0.375 square inches? Okay, so that tells us the sum of the area of the bolts that we're going to use to connect that thing have to equal 3/8 of a square inch. Okay? And then what we're probably actually doing is we're probably putting in enough cross-sectional area so we've got 3/4 of a square inch to give us a safety factor of 2. Okay? So if we find bolts that would give us 2 of them equal 3/8 of a square inch, we probably have our iron workers drop 4 bolts into that thing. Okay?
Can you give us an example and give us like 2 minutes to try and figure it out?
Yeah?
And then
Yeah.
check it.
So think again of this system, okay? Think of 4 bolts. There'll be circular bolts, okay? And you don't have to worry about buildup area for threads or anything like that, okay? This is bearing area is what I'll give you, okay? Let's say each of them have 3/8 inch diameter. Okay? And let's say the force applied on the beam, 7,500, so let's say 12,000 pounds. Okay? So yeah, you can take 2 or 3 minutes, work on that thing, and then we can talk about what values do you come up with.
P, right?
Force applied is the P. Yep. Yep. A is the area, V is your shear strength. How we doing? Getting values? Couple more minutes yet? Cut. Ready to try tackling this thing?
Sure.
Okay. So, what are we getting for values? Let's hear from some people.
108,650.
108,650?
That's what I got too.
What are your units?
PSI.
PSI. Okay. So we got 2 votes for 108,650. What else are we getting?
27,162.
27,162.
162. How about that one?
So different by a factor of about 4?
Yeah, it is.
Okay.
It's exactly the same.
What else we getting? Those are the 2 that people are getting? Okay. So let's talk about, so here's our basic form. Are there any changes that we need to make to solve this problem? No, it's set up for us, right? We have our force applied, and we're not given the area, but we're given information about our bolts that allow us to determine the area, okay? So what did you do? What's your force applied? 12,000 pounds, right? What's our area?
4 times pi 3/16 squared.
4 times pi times 3/16 of an inch squared.
That's for the 27,000.
Okay. What does that crank out to be?
IR squared.
It's about 0.44178.
I rounded it to 0.442.
0.44 inches squared?
Yeah.
Okay, that works for me. So then 12,000 divided by 0.44, right? Cranks out to that value. So, Zach, when you calculated yours, did you just calculate for 1 bolt?
Yeah.
Okay, okay. Yeah, so that was the little curveball that I threw at you, is to calculate that stress, make sure that you multiply your area by all 4 of the bolts, right?
So could you solve it for 1 and then divide by 4?
Yeah, yep, it'd be the same thing. Yep, that would be, I forget, who else said that they got the same thing as Zach? Cody? Did you get 108,650? Yeah, all you need to do is take that number, divide it by 4. I mean, there's rounding in there too, right? With that 108,000, but yeah, that's the only difference, which we hadn't done that before, right? So, Okay. Feel confident about those types of problems at this point? Okay. Then let's look at shear in beams. Okay, because that's where we have to take a little bit more of an intuitive leap. Okay, so we've got a 12-foot span. We're pinned on one side. We've got a roller support, so as this thing warms up and cools down, it can move around a little bit. And we're going to drop 400 pounds 3 feet away from the pinned support, and we're going to drop 600 pounds 8 foot from the pinned support. Okay? So what's the first step that we have to do?
And the change in
We want to sum up our forces, right? Make sure that this thing isn't going to start moving on us. Okay? Is anything operating in the X direction? We don't have any wind, we're ignoring friction, we're all of those things, right? So nothing in the X direction. What about in the Y direction? What do we have?
400.
And we'll say that those directions are positive for our X and Y's. Right, so we've got 1,000 pounds pushing down. So if that's the case, what has to be true about R1 and R2? If that beam's going to stay in place. They have to sum to 1,000 pounds, right? Okay? Now, to solve for R1 or for R2, which one do you prefer? You want to solve for R1? Okay? So we're going to take our moment about R2. And is everybody all right if we say clockwise rotation about our point is positive? If you like doing counterclockwise, that's fine. Just remember that anything I put up here positive will be negative on your paper. Anything I put up here negative will be positive on your paper. The magnitudes come out to be the same. Okay? So, if we're going about R2, how far away is R1? R1 is 12 foot away, right? And how is it trying to cause rotation about R2? It's doing positive rotation or negative rotation?
Positive.
R1's doing positive rotation, right? Okay. That's not good. Might be multiplication there. What about 400 pounds? How far away from R2? 9 feet. How is it trying to cause rotation? It's trying to spin things this way? Or is it trying to spin things this way?
Negative.
It's trying to do counterclockwise, right? So it's negative for how we've determined it. Okay, then we've got 600 pounds. And how far away is the 600 pound force from R2? 4 foot. Positive rotation or negative rotation? Also negative, right? Okay, so 12 R1 pound-feet has to equal That works out all right. 3,600 and 2,400. 6,000 pound-feet. Does that seem reasonable to everybody? 2,400, 3,600. Good? So if R1 is 500 pounds, what's the magnitude of R2? Also has to be 500 pounds. Does that physically make sense to us? 600 pounds, it's a little bit further away from R2 than R1 is, right? And it's got greater magnitude. So physically that makes sense, okay? But remember, we're interested not just if this thing is in static equilibrium, but what's going on as these forces are trying to shear this beam, okay? We also have to determine what is it going to take to make sure that this beam doesn't get ripped in half, okay? So we'll diagram where here is R2, here is R1. How do you want to move across the beam? You want to go left to right, or you want to go right to left? Left to right, okay? So we're going to go left to right. Is it all right to say that up is positive when we're talking about our shear? Okay, so when we get just to the right of R1, not even an inch away, okay? What's trying to shear the beam? It's the 500 pounds, right? Because remember, until we pick up the force, the beam doesn't know that there's shear occurring, okay? So we pick up the 500 pounds from the reaction. What happens when we get 1 foot away? Does it change? No, because we aren't introducing any other forces, right? But what happens when we get just to the right, not even an inch to the right of the 400-pound force? What's going to happen to our shear? We're going to get right to the right of the 400-pound force. We're not even an inch, not even a half of an inch. Just past it.
Would it go down to 100?
Yeah, why would it go down to 100?
Because it's 400 pounds of force pushing down and 500 going the other way.
Exactly. Yep. We've got 500 pounds pushing up on the beam. We've got 400 pounds pushing down on the beam. Okay? So it's going to truck along at 500 pounds until it gets to that 400-pound force, and then it's going to drop to 100. Okay? Then what happens? Do we have any changes over these 5 feet?
No, it stays at 100.
Yeah, it's going to stay at 100 pounds until we get to the right of that 600 pounds. Oops. Let's drop that down a little bit. What happens when we get just to the other side of that 600-pound force? What's our shear going to do? It drops that 600 pounds, right? Okay? And then what happens at R2?
Goes back up.
It picks up that 500 pounds from that reaction, gets back to a shear value of 0. Okay? Oops. So, what's our maximum shear? 500 pounds, right? And it truly occurs at 2 locations, right? It occurs from 1 to 3 foot, and it occurs from 8 to 12 foot. I know that it says minus 500 there, but remember, the beam doesn't care about positive and negative. Okay, the beam only cares about the absolute value of the magnitude, right? Remember last Thursday I said, doesn't matter if we try and rip the thing from below or if we try and rip the thing from above. If we exceed the shear capacity, our material is going to fail, okay? So, our max is 500 pounds. Where does our shear equal 0? And ignore the reactions, because we aren't interested in where the reactions are. Where does the shear equal 0?
4 feet from R2.
4 foot from R2, right? Good. That will become important when we pick up our next topic about bending. Okay? We find that our maximum bending moment occurs where shear equals 0. At non-reaction points where shear equals 0. Questions on this problem? Okay. We should look at a uniformly distributed load as well, so you understand how to use that. Do you want me to diagram it and you try and tackle it, or do you want to walk it through it together? I'm fine either way. Doesn't matter to me.
Walk through.
Okay. Okay, so this time we'll look at a 10-foot span, and 1 foot from R1 to 5 foot from R1, we have 400 pounds distributed over 4 feet. And then 7 feet from R1, we've got 600 pounds. Okay? So what do we need to determine first? We have to make sure that we're in static equilibrium first, right? Okay, and again, f sub x is going to equal 0. I know that's kind of an annoying step, but I don't want you to get lulled into a sense of security, right? Because once we get out in the real world, friction and wind and snow load and rain and all those things apply, okay? So we have to be aware of them. What about f sub y? We'll throw that in too, I suppose. What are our forces acting in the y direction? I'm sorry. I told you that we had 400 pounds distributed over 4 feet. Do we?
400 pounds
This would be 400 pounds, right? Because we've got 100 pounds per foot
per 4 feet.
acting over 4 foot. Okay, so we've got minus 400 pounds. Or did Zach say that we've got a total of 1,000 pounds, right? Because we've also got negative 600 pounds. What does that mean for R1 and R2?
They have to equal.
They have to equal that, right? How about moment? Excuse me. You want to go about R1 or do you want to go about R2? We're going to look about R1 this time. Okay. What does this thing do? What do we do with uniformly distributed loads?
Put it right in the middle
Of
of the 4 feet span.
of where the load's being applied, right? Okay, so we have 100 pounds per foot times 4 feet, right? So 400 pounds is the force. How far away from R1 is it?
3.
It's 3 feet away. Everybody follow what Zach did, right? So we put the 400 pounds here, right? So it's 2 foot from here, but we're looking